Hello everyone, welcome to Stat 310 Lectures 316. So today we're looking in a fair bit of detail at this generalized likelihood ratio test, which is in 9.4 of the textbook. And the basic idea is that remember that the likelihood ratio test was this most powerful test for the scenario where we had simple hypotheses. And now we want a result for general hypotheses, whether the H naught could be composite and so could the H1, and we want kind of a testing approach for that. And it turns out that there's a notion of generalized likelihood ratio test, which is very useful. And we're going to kind of see sort of how that. We're going to kind of see what that looks like in various examples, and it's something that we're going to kind of encounter throughout the course. It's going to be the basis of a number of other tests that we might look at that we're going to see for the remainder of the course. So this is going to be a very important lecture again, because it's going to build the basis for other concepts that or other tests that we're going to see later in the course. So to be clear here, these could be simple or composite tests, hypotheses. And obviously we are assuming throughout that the intersect of these two sets is empty, so there's no overlap between the null hypothesis and the alternative hypothesis. So the GLRT statistic, so firstly we always need a test statistic. So the GLRT test statistic is very related to the likelihood ratio test statistic, but now because we have a whole set, we take a maximization. So here, the maximization for the numerator is just over the null hypothesis, theta and theta 0. For the denominator, rather than taking it just over the alternative, for convention, and we'll see it's going to make kind of calculations, and then we're going to show something about the distribution, it's going to be a lot easier if we take the union of theta 0 and theta 1. So to take a concrete example, which we started in the previous lecture, we're going to let H0 be theta equals theta 0, which is what has kind of come up frequently. And the alternative to begin with is just theta not theta 0. So that's the whole real line except for theta 0. And this is kind of a nice example to begin with, because we kind of introduce concepts that we've seen before. So because the numerator, the null hypothesis just as theta is 1 point. The numerator, if you maximize over 1 point, you just take that point. But if you maximize for the denominator, you're maximizing over the whole real line, which is why it's convenient to take the union of theta 0 and theta 1. This just becomes the maximum likelihood estimator. So recall that from chapter 8. And one of the things I've said a number of times is that the calculations are not actually overly different from what we've already done in chapter 8. It's just that we're building a different kind of framework to look at this. So here we've got, remember that theta hat ml is equal to the argmax. Okay, so here we're assuming that the xi's are independent, and so the argmax, remember, the theta hat ml was given by this formula. So let's see a couple of examples. So here we've got the standard normal where sigma squared is known and fixed. And our H naught here is mu equals mu 0, and H1 is mu not equal to mu 0. And so the so remember that we're deriving this for the case where the composite hypothesis is mu not equal to mu 0. But you can extend a lot of this framework to other settings, and we're going to do that potentially not in this lecture, but in other lectures in the future. So let's look at this setting. So we know that the PDF for the normal, here we're treating the sigma squared as a constant. Okay, so this is what the PDF for the normal looks like. So if we were to calculate the generalized likelihood ratio test statistic, you plug in mu equals mu 0 on the numerator, and then you plug in mu equals mu hat ml on the denominator. Okay, and so what is mu hat ml? So hopefully this is something that's almost second nature to you by now, so that mu hat ml here is just x bar. We've done this calculation a couple of times, so I'm not going to go through it here. If you do go through maximum likelihood for the normal distribution, that's just equal to the sample mean, and that's also the method of moments estimate. So that's what we plug in here. So our gamma hat here is equal to Okay, so now if we expand this out a little bit, clearly these this numerator completely cancels, and we can kind of rewrite everything because we've got the product of exponentials. You can rewrite that as the sum of the product. Okay, and so once again we've got the quotient of two exponentials, so that's just the you can just subtract the exponent. And we can do a little bit more rearranging to kind of make this look okay, and so so with some cancellations, the xi squareds will cancel. Okay, and then when you bring the sum through, just going to get n times mu 0 squared minus 2 x bar times n, mu 0 minus x bar, and then minus n x bar squared. So we can bring out the factor of n. So it kind of works out nicely to look exactly like x bar minus mu 0 squared. So you can write out the GLRT purely in terms of the x bar, purely in terms of the statistic x bar. How do we... And then the question is, how do we turn this into a test? So we have clearly the size of the test is alpha. And the other thing to, remember that so the bigger, so remember this is a likelihood ratio, so a likelihood that favors theta 0 as opposed to the alternative is going to be more favorable to the null. The bigger gamma hat, the more likely to accept or not reject H0. So so the acceptance region that we have here is that if gamma hat is bigger than or equal to some c, we accept H0, that's our acceptance region, and our rejection region is gamma hat has to be less than C. And then, the question is, what is C? And it's clearly going to depend on alpha. And so you can kind of see from here we have that. So in our example, gamma hat is okay, so like you can see that the closer to like the closer mu is to mu 0, the larger this GLRT statistic is. And then so we'll discuss later how we find threshold C, because this is going to come down to what is the distribution of that statistic gamma hat, or lambda hat, sorry. Let's do another example. Here we've got x1 through to xn is as an exponential distribution with parameter lambda. So we're again going to have the h naught as lambda equals to lambda 0, and h1 lambda not equal to lambda 0. And remember that it's just lambda e to the negative lambda xi, and here clearly we're assuming that all of the xi's are bigger than or equal to 0 here, because it's from an exponential distribution. So the lambda hat we have here, the statistic is the product of these two PDFs evaluated at, or the ratio of these two likelihoods evaluated at different points. Okay, so this is what the ratio looks like, and then the question again is, what is lambda hat ml? And again, this is where we use the calculations that we already did from chapter 8. You can see that the lambda hat ml is again equal to 1 over the method of moments estimate, which is 1 over the summation of the which is 1 over 1 over n, the summation of xi. So that's what the lambda hat ml is, and so okay, so this is what the this looks like, and then again, you kind of get some nice you can get some nice simplification here because of the fact that you're taking products of things and you have exponentials in there, and so you get okay, and then when you take the sum inside, this gives you okay. So this is e to the negative n lambda 0 x bar minus 1. So we'll leave it at that for now. We'll go back to this expression shortly. And then once again, the form of the test. So once again, we can see that this works out nicely because it's just in terms of the x bar. So once again, we're going to have that if the GLRT is less than or equal to C, we accept or not reject H naught gamma hat bigger than C, we reject H naught. And once again, we can see that here you can kind of plug that all in and see that this is the gamma hat that we get earlier here, and if x bar is close to, or we can say if x bar times lambda 0 is close to 1, this gamma hat gets smaller. Okay, and that's consistent with that. So the next question is, how do we find C in terms of alpha? And this kind of leads to the next kind of key result from section 9.4, distribution of gamma hat. So remember again that we're going to go back to the general form of this this result first, or this statistic. So we're going to let D, this is going to be related to the so-called degrees of freedom. I'm going to use a slightly vague definition here. I'll tell you what it is in various examples. D is the dimension. So here the dimension of S loosely is, there are some strict definitions of it, but I think the easiest way to interpret it is the number of degrees of freedom or parameters that define the set S. So for example, if you're like the examples we've seen so far, if your theta 0, big theta 0 is just 1 point, and then your theta 1 is the real line except for 1 point, then the dimension of the union of these two is just equal to 1, because this is just the real line. So for the real line, you can that just has 1 degree of freedom, because essentially any number on the real line can be encoded by 1 parameter theta. But on the other hand, the dim of theta 0 theta 0 is just equal to 0 in this case, because theta 0 is just 1 point. So there's no degrees of freedom here, because you're kind of the theta 0 is just completely defined by one set. So it's a little bit vague, but for all the examples that we see in this course, this notion of dimension is going to be pretty clear, that it's just in some sense the number of parameters that you that define the set. And when you do that maximization, it'll be pretty clear how you how many free parameters you have. But we're going to see that in various different examples. But for this for the example we see today, the d, which is the difference of these two dimensions, is 1. So we can say that d equals the dim of theta 0. This thing is equal to 1 in this so this is in the case where okay, so this is the kind of the next key result that this is not where we're not going to prove this, but we're going to see this in a couple of examples under standard regularity conditions, and we're not going to verify these. For all the examples where you need to use this, this is going to be true. So if you look at the -2 times the ln of gamma hat, that's going to converge in distribution to the chi-squared, where d, the chi-squared with degrees of freedom d, where d equals this dimension. Minus dimension of theta 0. And this is as n goes to infinity. So like all things, it's very hard to prove the to find a form for a close form for the distribution for finite n, but we're able to do this for general n as n goes to infinity. And this result is very useful. So gamma hat here, lambda hat is the GLRT statistic, and this is what we get for the so this is what we get for the distribution. So let's take a look at this in action. So if we go back to this first example, we'll see that things kind of work out really nicely here. X1 through to xn's mean mu variance sigma squared. H0 is mu equals mu 0. H1 is mu not equal to mu 0. So we learned from before that okay, so this is what we got for the form of the likelihood ratio statistic here. And now let's look at -2 times ln of lambda hat. That's just equal to n times x bar minus mu squared over sigma squared. And also note that x bar, as we know, is normal with mean mu and variance sigma squared over n. So therefore, it clearly follows that square root of n times x bar minus mu over sigma is in distribution equal to normal 0, 1. And so if you square that whole thing, that's in distribution chi-squared 1. So just like a lot of asymptotic results, in the special case where you look at things being normal, the asymptotic results holds exactly. So here, as we derived earlier, d equals 1 because there's 1 degree of freedom here. And so this shows that n times x bar minus mu squared is sigma squared. So again, now to just relating this to, how do we find c? How do we find c? So remember that we said that if gamma hat less than or equal to c, that's the acceptance region. And then if gamma hat's bigger than c, that's the rejection region. Okay, so we know that -2 ln of gamma hat is approximately chi-squared d, where, if n large. So again, we kind of use an approximation here. So therefore, we're going to actually say that sorry, there's no n here. That if negative 2 ln gamma hat is sorry, it's the other way around, isn't it? Let me make sure I change that throughout. It should be the other way around here. Because clearly, the bigger the numerator, the more likely you are to accept it. So I just want to make sure I did this correctly throughout. So this is not correct. This is the other way around. Yeah, so it's good to make sure you do that correctly. So I did it correctly for the first example, but I flipped the signs for the second example. Okay, so clearly then we're saying that if negative 2 less than or equal to negative 2 ln c ln c, then this is you accept h naught, and you flip the sign because it's a negative now. Negative 2 times ln of gamma hat is less than, or sorry, now this is going to be bigger than negative 2 ln of c. You reject h naught. And so the basic idea is that, we have the chi-squared distribution here is, this is a distribution that's positive, and the distribution looks something like this. So if this area is alpha, I've drawn here the rejection region. So similarly, you could draw, if you're more comfortable with things the other way around, I'll also draw the acceptance region. So if this area here is alpha, this area here is 1 minus alpha, this is the acceptance region. This is the acceptance region for IE. So if this is our C, we're saying, or this is not our C, this is negative 2 ln C. So negative 2 ln gamma hat is going to be less than or equal to negative 2 ln C. That's the, this is the acceptance region. Okay, and so I'm going to use this notation chi-squared of chi-squared d alpha for this here. Like, we'll say that just like I use the z-score for the chi-squared for the z or normal table, we're going to say negative 2 ln c equals to chi-squared d alpha. So this is where we just look up the table to find that value. And so if we wanted to find, negative 2 ln has to be less than or equal to chi-squared d alpha for that critical threshold, which is the same as saying that this gamma hat should be bigger than or equal to e to the negative chi-squared d alpha over 2. Okay, and so this is the acceptance region, and you can work out the rejection region as well. And you can actually show that this is, in fact, equivalent to standard z-test. So if you wanted to, if you did it kind of the standard way with the z-test as we've always done, these two, the likelihood ratio test and this are equivalent. So this is this I'll leave to you as an exercise. You should be able to relate using the relationship between using the relationship between the chi-squared and the z. You should be able to show an equivalence between these two tests, the z-test and the and this GLRT, or which uses a chi-square distribution. And I guess just to write this out, so we know that gamma hat's equal to so this is equivalent to saying that it should be bigger than or equal to and so this is exactly the same as saying that is less than or equal to and here we've just got the degrees of freedom is just 1 here, because clearly we're in this scenario where d equals 1. Okay, so this is kind of just a check of what we're doing. So this is the acceptance region. In terms of x bar. So let's just look at this second example just to make this idea kind of concrete in our minds. So we have that so in this case, this is the expression that we have for lambda hat. So let me try to remember that. So this is the expression for lambda hat that we have. And if we look at -2 ln of gamma hat, that's just equal to it's going to be n n times 2, and then lambda 0 x bar minus 1, and then minus ln x bar lambda 0. And we claim that -2 ln converges in distribution to chi-squared 1. And again, the reason why that's the case is, we can use the Taylor series. So this is not something you have to do. I just want to just give you an idea of why this generalizes. So it's a bit like how the central limit theorem and other results generalize beyond the normal distribution. So to show this, we can use the Taylor series. So so we use the Taylor series of expand Taylor series for ln x around x equals 1. So if you plug that in here, so that's basically saying that lambda 0 x bar should be close to 1, which is what we kind of get under the null hypothesis. All right, and actually one thing I should mention is that is only the distribution. I should say this, sorry, that's a mistake. So this is the distribution under H naught, which is under the distribution of H naught. So whenever I talk about a test statistic, I'm only talking about the distribution of that test statistic under H0. So yeah, again, I'm not going to kind of sketch this out completely, but if you show that that's the under H naught, so this is all under H naught. Then you can see that that this is approximately the same thing. So you can see that what you'll get is something that's just going to be a square. It's going to be n times bar over 1 over lambda 0 squared over 1 over lambda. And then this is this converges to chi-squared 1 by the CLT. So again, I'm not going through that Taylor expansion explicitly. It's something you can check if you do the Taylor expansion of ln of lambda 0 x bar. You can check that that's exactly what you get. And so once again, you can see that the test would say that if negative 2 ln of gamma hat is less than or equal to negative 2 ln of c, then we reject H0, accept H0. Accept H0, and then clearly we have that negative 2 ln c again is just this chi-squared 1 alpha quantity that we saw earlier. Okay, and so that's equivalent, same as using the CLT. Okay, so that's kind of just demonstrating the GLRT in the case where we have the test, the null hypothesis is theta equals theta 0, and the alternative is theta not equal to theta 0. So what I'm going to just do to in the last sort of 10-15 minutes of this lecture is move on to another set of examples in 9.5, which is if you have so the multinomial distribution, and this is kind of an important example. So so I'm just going to go through it in a bit of detail. Some of you may not have encountered the multinomial distribution before, but it's reasonably intuitive. So I'll just kind of give a bit of a background to it. So you have here you have m categories. So you have m categories, and a good example is like a blood type. There's I'm not exactly sure how many blood types there are, but each person falls into one of some number of different categories. So we've seen this for like if m equals 2, this is just the Bernoulli or binomial, or I should say this is just the binomial. Okay, but here we're talking about generalizing the binomial to more than 2 categories. So the idea here is that we have so we have two M categories, and then we have N samples or data points. So here our data is xi is the indicator so the data that we observe here, which can be thought of as like a I'm going to use the notation here as O1, O2 up to OM. This is the number of xi's in category 1, and then similarly number of xi's in category M. So we have that xi, it denotes which category does sample fall in. Okay, so you basically start with x1, x2 up to xn, where n is the sample size that we're used to seeing. And then you can convert that into, this gets converted into O1, O2, which is the number of observations in each category. So we can say that OJ summation I equals 1 to n, and it's the indicator that xi is in category J. So this is just saying that xi belongs to category J. And so the distribution here is that so we let P1, P2 up to PM denote probability of being in each category. Okay, and so let Pj of so and we're going to let theta encode that so we have that so PM of theta, probabilities of being in a category in terms of theta. Okay, and so the overall likelihood, or we can say that f of O1, O2 up to OM in this case is just Yeah, this is potentially a little bit unintuitive, but we'll okay, so you just take the product of these various probabilities. And so just to make this a little bit more explicit, so in the Bernoulli case, or in the binomial case, I should say, I mean, you're used to the probability being like f of, say, O1, O2 is equal to, n factorial, O1 factorial O2. If we were to rewrite this out, it would just be P1 to the power of O1 times P2 to the power of O2. But what's going on here is that we have this constraint. Remember that we have to have that P1 plus P2 equals 1. And in general, P1 plus P2 plus PM is equal to 1. And then we also have that O1 plus O2 has to equal to N. So this is and this is the same as in general. O1 plus O2 plus OM is equal to N. And so if you rewrite this out, then we get that f of, so O1 here is going to be just the summation I equals 1 n of the indicator that xi is equal to 1. And O2 is equal to the summation I equals 1 to n indicator xi equals to 2. Often we refer to this in the case of the binomial as 0 and 1, but it's effectively the same thing. And so this just gives you the formula of this just gives you the formula f of O1, O2 is just n factorial, O1 factorial, n minus O1 factorial, and then P to the power of O1, and then 1 minus P1 to the power of n minus O1. And that's exactly the formula you get for the binomial distribution. So this is clearly just an extension of that binomial distribution. So we have that is equal to O1 factorial up to OM factorial, and then P1 theta to the power of O1 up to Pm of theta to the power of OM. But then we also have these constraints that summation j equals 1 to m of Oj should be 1, and should be n, and then the summation j equals 1 to m of Pj of theta should be equal to 1. Okay, and so this is exactly the form of this this distribution. And so how does this exactly relate to testing? So relating to, so we'll continue this in the next lecture. So relating this to the test and to the generalized likelihood ratio test. So here you're typically going to have that H naught, which is just that Pj is equal to Pj of theta. This is just some parametric encoding. And then H1 is that Pj is not equal to Pj of theta. So basically Pj's can be, so this is any set of probabilities that are not defined by Pj of theta. And we will see an example of this shortly. So we have that theta 0 is equal to the set Pj of theta such that theta is in R. And then theta is 0. And then we obviously have this constraint. Summation j equals 1 to m of Pj of theta is equal to 1. And if you take the union of this is just as Pj, with the only constraint being that some j equals 1 to m of pj is equal to 1. Okay? So in some sense, we're placing no constraints on this. And so in the last 5 minutes or so, one thing to note here is that the dim of theta 0 is equal to 1 since defined by parameter theta. And then the dimension of theta 0 union with theta 1 is actually equal to m minus 1 since we have parameters p1, p2 up to pm. So that's m parameters, but then we have constraint summation j equals 1 to m of pj equals 1. So you can kind of re-encode this in terms of the parameters p1, p2 up to pm minus 1. And then the probability of the last category is going to be 1 minus p1 minus p2 up to pm minus 1. So this is why the dimension here is m minus 1. And this is going to be useful when we talk about the GLRT in the test statistics. So now let's talk about what that GLRT is. So so in this case, because we already, this is a little bit different from some other examples because we're looking at this distribution as a whole. And so the likelihood really only has kind of one, it's like one sample, but of the whole multinomial distribution. So this is a little bit different. That's why we don't have the product here, because the whole distribution is determined by that one formula. And then this is going to be f of xi, and then this is in terms of p1, p2 up to pm with that additional constraint. So, and so one thing you can check is that so this is going to be a little bit different again from what we've seen earlier, because this is a slightly more complicated likelihood ratio test where we're going to actually get f of xi theta hat ml, and then on the denominator we're actually going to get f of xi and then p hat 1 ml, p hat 2 ml up to p hat m ml. Okay, and so what does that actually mean? So remember that f of xi theta is equal to n factorial over O1 factorial up to OM factorial, and then P1 to the O1 times PM to the OM. And then, and these are functions of theta. I'll be almost done and we'll finish this with an example in the next lecture. P1 of theta to the power of O1 up to PM of theta to the OM. And so theta hat ml equals to the argmax of theta of f of x, sorry. This should not be xi anymore. f of x theta. And then p hat ml, you can check that this is p hat ml p hat, or we'll say p hat j ml. This is something you can check. If you don't place any constraints on that, is just going to be equal to oj over n. And that kind of makes intuitive sense. This is just proportion of sample in category J. Okay, and so we'll end this today, and we'll continue with the discussion in the next lecture. So we'll go into this. A lot of what I've said in the last 10 or 15 minutes is potentially a little bit new, and we're going to delve into this in a little bit in more detail in the next lecture. Okay, thanks very much for your time. Bye.